Hey, welcome back to Fat Mama Physics! Thank you for coming back to 6.1, Part 2, which we talk about scale diagrams and enlargement. So blowing small things up to a bigger picture on a diagram for you to analyze, especially when you're trying to see very small things. A microscope is a very good example, blowing something up. I apologize, the last video got a little long and I took a long time to talk about the game. Promise the next one I will definitely make that one shorter. Even though I like that game more. Too bad. So, to make up for it, I guess I will try to keep this video very tight. So, let's get going with example 2. Using corresponding lengths to determine the scale factor. And this, I have an actual mosquito. The actual length of a mosquito is 12 millimeters. Oopsies. The drawing of the mosquito is 4.5 centimeters. Find the scale factor. Oh, hey, look, the question even reminds us that we have to make sure that the lengths are the same units. So first things first, we need to convert the drawing of the mosquito, 4.5 centimeters, into millimeters. So to convert centimeters to millimeters, remember what it was? If you were thinking of multiplying by 10, you are correct. Okay, so then we have the actual mosquito length, the length of the mosquito on the paper as 45 millimeters. So when we calculate scale factor, remember, it is the copy that we have on the diagram over the original size. Is always that way to figure out the scale factor. Something over the original size. Something over the original size. So the length on the scale diagram for a mosquito is 45 millimeters. The actual length of the mosquito is 12 millimeters. So we quickly plug that into our calculator. 45 divided by 12 is 3.75. That is our scale factor for our mosquito. For our mosquito diagram. Alrighty, notice again the scale factor is greater than 1, which makes sense because this is an enlargement in which the actual the copy of the picture itself is bigger. Going down to the next example, we have a photo of Einstein. Determine the length on the scale diagram, multiply corresponding length. Okay, so in this example, we are looking at what happens if we know the scale factor and we want to, say, figure out the original size or the copy size based off the scale factor. So let's read this. Determine the length of the scale factor, multiply corresponding length on the original diagram by the scale factor. So here I have a photo. It has dimensions of 9 centimeters by 6 centimeters. Here we can label it, and I'm assuming the length is going to be longer here. So the photo is to be enlarged by a scale factor of 3.5. Yes, blow up Einstein in your room. Find the dimensions of the enlargement by multiplying each dimension by the scale factor. So what we're doing right now is we have a small picture of Einstein. We want to make him bigger by a factor of 3.5. So what we want to do is we want to make sure that every side is scaled the same way. So we don't have Einstein all squished together. It's kind of when you're making a Word document and you're trying to make a picture bigger, if you drag just the horizontal bit, you kind of like make him look fatter, make your picture look fatter. If you drag the vertical, then you scale the vertical only and make someone look very skinny. What we want to do with scale factor is we want to make sure both sides are scaled equally as much. So here we have the length. To enlarge the length, so the vertical one, we need to take the scale factor and multiply by the corresponding length. You might be wondering, why do I do that? Well, let's take a look at the equation above. The scale factor here is length on a scale diagram over length of the original diagram. You know what? Let me simplify this into a simple equation for you to use. So I wrote here SF for scale factor, and abbreviated, is equal to your copy divided by your original. So if we are going to apply that in example 3, we want to figure out we have the scale factor, which is 3.5. We have the original. We want to figure out how much we need to make our copy. We want to make Einstein bigger by 3.5. So that's the copy that we're going to create. We're going to make from our original. And if we just rearrange this equation, so if we want to solve for copy, imagine copy is a variable. We have to multiply both sides by the original size so that we get the size of your copy is going to be equal to your scale factor times your original. Okay, so based off the equation, that's where it comes from. Intuitively, you can think of it this way. If you have the original size and the scale factor, to blow it up, you have to take this, multiply by the scale factor to see what you get as a result. So let's take 3.5 times 9 centimeters, 3.5 being your scale factor. We get 31.5, meaning if we have to make Einstein bigger, this vertical length would have to be 31.5 centimeters instead. The scale factor in the width, for the width, is also whatever the width times the scale factor 3.5, that is a total of 21 centimeters. So the dimensions of the enlargement we have is 31.5 centimeters times 21 centimeters. It doesn't matter which order you write it, it's just dimensions. You know, one is the other one based off of what you see in the picture, okay? Example 4, drawing a scale diagram that is an enlargement. On the grid, draw a scale diagram that's L shape, and we have the scale factor of 1.5. Determine the length of the line segment on the scale diagram by multiplying each length on the original diagram by 1.5. So essentially what we're doing is kind of like the Einstein drawing. We have a small drawing we want to make bigger, and you're going to draw this on this 1 centimeter grid. So this is a great opportunity for you to try yourself by pausing the video. Okay, so I will do this one together with us. So on the bottom here, there's a guiding set of numbers, because notice in our diagram, we have numbers that range from 1 centimeter, 2 centimeters to 3 centimeters. If we take them and we multiply them by 1.5, so for example, 3 times 1.5, we're going to get 4.5 centimeters. 2 times 1.5 is going to give us 3 centimeters. 1 times 1.5 is going to give us 1.5 centimeters. So on this grid, imagine every box is represented by 1 centimeter, meaning that I'm going to draw the top. I'm going to start with the, you know what? I'm going to start with the length, 3 centimeters, because I need to blow that up all the way to 4.5 centimeters. I want to make sure I have enough space. So let's start on this side. So we definitely have enough space. We're going to go 1, 2, 3, 4 for the length, but 4.5, so about right there to there is going to be the length of this 3 centimeters right there. For 1 centimeter, it gets blown up to be 1.5, so that's going to be there and a tiny bit there. Okay, so that's 1.5. Then we're going to go down 2 centimeters. Down 2 centimeters, 2 times 1.5 is 3 centimeters, so that's 1 box, 2 boxes, 3 boxes. Okay, next up we have another 2 centimeters blown up by 1.5. We're going to also go by 3 boxes. Careful, this is at the halfway mark, so we got to go halfway points. We have to go to the next halfway point. Halfway point, 2 halfway points, 3. Okay, so that's 3 centimeters. Next up we have 1 centimeter down, which is going to be 1.5 centimeters scaled up. So that's 1 and 1.5, and it should reach the bottom, because notice the bottom is a flat line, which is 3 centimeters, so we double check this whole way here is 4.5 centimeters. 1 centimeter, 2, 3, 4.5. Perfect! There we go. Let's label our sides. This is 1.5 centimeters. This is 2 times 1.5, 3 centimeters. This is also 3 centimeters. 1 centimeter gets blown up to 1.5. This bottom here gets blown up to 4.5 because it was originally 3. And last but not least, this is 4.5 centimeters over here. There you go. Hopefully you had something that looks like this. It does not matter where this is on your little diagram, but your shapes should look the same. Here, I can even put in some of these boxes to show that these should be 90 degrees to each other. Okay, there you go. Oh, one more over here. Perfect! Hey, we're almost done. We got one last example to go. So guess what? I'm just going to quickly show you what this table means, and maybe you get a chance to figure this out for yourself. So here I have a table. Here we have the original. This is the copy, and this column tells you the scale factor. So what you want to do is, based off of these numbers, try to figure out the missing one, the missing box. Now, I don't highly endorse this because I hate triangles. These triangles over here that kind of tell you what to do, it definitely messes up my students when they come into physics because they think triangle all the time and they can't apply the whatever equation they need to a new problem. So it becomes fixed. But if you're just starting out and you're kind of trying to make things, you're trying to figure things out, this is not a bad way to go. So how does this triangle work is, if you multiply the two bottom, it gives you the top. So scale factor times original gives you what you need for your copy. And vice versa, if you have copy on top and these on the bottom, it means if I take my copy and I divide it by the scale factor, it's going to give me the original. Same thing if I do it the other way. If I take my copy and I divide it by the original, it's going to give me my scale factor. So top divided by bottom gives me the other one, top divided by bottom gives me the other one, or bottom two multiply each other because they're side by side gives me the top. That's how the triangle works. If that really helps you for now, sure, use it, but I personally don't like it. I would rather you use the equation here as a way to figure it out, or use conceptual understanding to figure out where the numbers would go in terms of ratio making, okay? Either way, whatever way you use, guess what? This is a good time to pause the video for you to try to fill out the table. Okay, now I will do it for us. Okay, so I have the original, I have the scale factor. I want to find the copy. So if I'm getting scaled up, I'm going to need to multiply my original by my scale factor to give me my copy. So here, let me remind us, my scale factor is copy divided by original. Okay, ORI for original. So if I take scale factor multiplied by original, it gives me my copy. So 3 times 15. That's going to give me 45 centimeters. And notice, whatever I get for copy, I have to match my units in my original and vice versa. Oh, hey, we have the same situation below. We have the size of the original. We need to scale it up by 15 over 4. So that's just 8.8 centimeters times 15 over 4. You can just put that into your calculator, or if you want to, this is technically 0.8 centimeters times 15 divided by 4. 0.8 times 15 divided by 4. That's what I put in my calculator. That gives me 3 centimeters. Next up, we have length of the original. We have the copy. We want to find the scale factor. I'm going to use a different color pen because we're doing something different now. So to figure out my scale factor, which is this guy, I need to take my copy divided by my original to give me my scale factor. My copy is 75 centimeters divided by my original. Notice they have the same units, which is good, same units. I get 30 for my scale factor. Last but not least, I have another situation here. I have my copy, I have this guy, I have my scale factor, but I don't have my original. So I have to rearrange this equation a little bit, okay? And if you kind of think about it, I kind of have to swap original and scale factor in a bit. So if I want to write this out, here, let me show you how it would look like using algebra. C for copy, O for original. So to get, what do I want? Original onto one side of the equation. To the top, I multiply both sides by my original. I get SF times O is equal to my copy. Okay, this is SF times O gives me copy. Then I divide both sides by my scale factor to give me my original is equal to copy over SF, which is my scale factor. If you use your triangle, then it would be this one. Copy divided by scale factor equals the original. But it's almost like you take your copy and you kind of divide it by your scale factor to scale it back down. To divide by the scale factor, it's kind of like scaling down to your original, okay? So I take my copy, which is 45, divided by my scale factor, 3.75, And I get 12, which is my millimeters. And guess where you saw this number before? With the mosquito question. So that was it would be a good way to check your answer by going back. Okay, so I think this is it. All right, there you go. That's it. That's enlargements for you. I thank you for watching, and you can join us back for reductions, which is taking a big thing and scaling it down on paper, which we're going to talk about other cool things. So thank you for watching. Good luck, Fat Mama Physics, signing out.